Hello there, I am Wasim Alexan from the German University in Cairo, and I attended today the European Wolfram Technology Conference in Frankfurt. It was amazing. I got to hear so many presentations, and I had the chance to give one also. It was about cooperative communication systems and how we can actually model them and simulate them in Mathematica. More than a year ago, I started a PhD program at the German University in Cairo. For some reason, most of my colleagues, if not all of them, decided to use a different piece of software to carry out the research. But I decided to try out Mathematica. My professor has been using it for such a long time, and I thought I'd use it. So today I'm trying to introduce the idea of modeling and simulation of a cooperative communication system. The idea is rather simple. Modern cellular networks are actually facing huge increases in multimedia services. They're supposed to be that require higher data rates at an adequate quality of service. One way of actually doing so would be employing multiple input, multiple output systems, MIMO systems. This, of course, is rather successful. One example would be the new Galaxy S5 by Samsung. It has more than one antenna that could actually handle this. Another way would be to introduce cooperative communication system. The basic idea is that we have a system We have a system composed of one source node, one destination node, and an array of relay nodes, where the relay nodes try to assist the source node in delivering its message signal all the way to the destination node. By doing so, well, the source node would actually try to send this message signal, and in its way, it's multiplied by the channel fading coefficients, and then an additive white Gaussian noise is added to it. At any given relay node, this is given by equation 1, the received signal. And at any relay node, you have to follow, or you can follow one of two techniques, either an amplifying forward technique, where you simply take the received signal, amplify it, and then forward it to the destination node. The other way around is actually to use a decode and forward mechanism, where you receive the signal, try to decode it, and estimate the original X, the sent message, and then forward it to the destination node. At the destination node, it's pretty easy. You just follow a simple combining rule, as this one in equation 2. And this results in good performance, but the problem is that activating all the relay nodes would mean that each relay node would have to forward the message signal or forward the signal it has at different frequency or at different orthogonal frequency channels. This results in a reduction in spectral efficiency. So the best way would be not to actually activate all of them in relaying, but simply to have an algorithm that would select some of them to do so. This is actually what we're trying to do. And we decided to use a quantized reliability relaying scheme. And it simply says that the way to select and activate the relay node is based on calculating the log likelihood ratio of the received signal at any given node. And this basically, or ultimately, depends on the real part of the conjugate of the complex channel fading coefficients multiplied by the received signal. Simply put, assume we're following a decode and forward mechanism where we try at every relay node to receive the signal here, decode it, estimate the original message that was sent by the source S, and then forward it again. If we're using a binary phase shift keying modulation scheme, this would simply be the following. If you have a signal like this one, 10100, using BPSK or binary phase shifting would mean that every 1 is encoded as a positive 1, every 0 is encoded as a negative 1. While utilizing our quantized reliability relaying scheme, does it in a little bit different way. So every 1 would be encoded as a positive delta, while every negative 1 would be encoded as a negative delta. And instead of just having this threshold in the middle, would actually have two different thresholds, positive eta and negative eta. This can be seen in the next scenario. So in the first scenario, if we get a received bit anywhere above or beyond the positive eta, it would be automatically encoded as a positive delta, where this positive delta is a regenerative symbol that the relay node would be activated in such a case and would actually relay the message received to the destination node. The second scenario is where you would have the received bit anywhere less than or having a value less than negative eta. In such a case, you would automatically encode it as a negative delta and again forward it to the destination node. The third scenario is where you would get the received bit anywhere between the positive and the negative etas. In such a case, you would not actually activate the relay node. You would deactivate it, not use it, not select it, and will not participate in assisting the source node in delivering its message signal. Such a system we can measure its performance using bit error rates. This curve simply shows how many errors we have in the bits we've tried to send and how the bit error rate changes with increasing signal to noise ratios. In the upper one with the less performance bit error rate, we can see the usual one where we would be using decode and forward, adding all the different path or all the different relay nodes and summing it at the destination node, getting their value. While the other one, which shows better or improved performance where we have less bit error rates, is one for the proposed QRR system. Now, for simulation purposes, we assume that we'd actually know the channel fading coefficients, but in real life, between any two nodes in a cooperative communication system, we don't really have the channel fading coefficients. And one way of acquiring these would be to follow a channel estimation algorithm. And its idea is very simple. It goes as this. The source node sends a ready-to-send pilot message, where this pilot message could be composed of any training sequence or any sequence of bits. The same sequence of bits is saved on all other nodes. So when the source node sends a sequence of bits to, for example, these two relay nodes, they compare the received training sequence or pilot sequence with the pre-saved sequence at any of them. By comparing the differences or getting the difference and comparing the two sets of the received and the one it's saved on it, it can actually estimate the channel fading coefficients between these paths from the source to each of the relay nodes. At this point, the relay nodes would do the same. They would send the training sequence to the source node, repeating the same procedure for all nodes in the cooperative communication system, allows all or any two given nodes to estimate the channel fading coefficients between themselves at any given point in time. For the channel estimation, we have here a curve showing in black the actual or the known channel fading coefficients and the estimated ones. As you can see, as the SNR increases, the differences between the estimated channel fading coefficients and the real ones or the known ones decreases significantly until they actually match up at about 30 decibels here. While this curve shows normalized mean square error between the estimated channel fading coefficients and the known ones. This is actually it. Thank you very much.